All right. Hello, everyone. My name is Austin Harris, and I'm here with
Hector Suarez.
And today we're going to do a quick presentation over polynomials and FFT. So to quickly go over what we're going to talk about in the presentation today, we have just a brief overview. So first, we're going to talk about what a polynomial is, and polynomial interpolation, and then we're going to talk about the discrete Fourier transform, and then we'll move on to what is the fast Fourier transform, and how polynomials relate to FFT, and then we'll go into the benefits of FFT over discrete Fourier transformation. So, and then finally, what are some applications of FFT?
All right, first of all, what is a polynomial? We have to first discuss what a polynomial is, because polynomials, I guess FFT depends on polynomials. So let's first define what a polynomial is and show you some examples of polynomials. A polynomial is in the variable x over an algebraic field f represents a function as a formal sum. And you can see the formal sum. You have a function of x equals a of j times x, and where your polynomial is the a term. And later on, we'll be multiplying many polynomials together, and this is why we have the big O notation at the very bottom. When you multiply two polynomials, on average you'll get big O of n squared running time. And next we have polynomial interpolation. Now, why is this important? Because polynomial interpolation allows us to extract the coefficients of our function. And for example, we have, and you'll see in the next slide, we'll have a picture of point value representation of a polynomial, and how we work backwards to extract we have a fitted curve and we have the function, and then we want to extract the polynomials from that function. Now here's a visual representation of point value representation of a function, where the points here are the red dotted, the dots on the function. Here on the left we have on the left side of this image here, we have the points. We have a matrix of points, and then another matrix of the polynomials. I'm sorry, the coefficients. And then on the right side is the function. All right, and one of the big questions that we'll be discussing is, why is the FFT important? And that is because it is able to multiply these polynomials very fast. And can we do this? Can we do this very quickly in linear time, from coefficient form to point value form? And that is, the answer is yes. If we are very strategic about choosing our evaluation points, in other words, we choose the complex roots of unity as our evaluation points. All right. Well, first of all, what is a complex root of unity? Complex root of unity is a complex number omega such that omega raised to the n equals 1. And our book says that there are exactly n complex roots of unity for k equal 0 all the way up to n minus 1. And now let's consider Euler's identity, and we can rewrite this complex root of unity in a different form. And here in the next box that's highlighted is the principal nth root of unity, and we're just expressing either the I in terms of using the Euler's identity. And here on the bottom right hand side, we have an image that shows us where the complex roots of unity are 1, and it's along the quote-unquote y-axis, the horizontal axis. And throughout this presentation, we're going to assume that n is an exact power of 2.
So now I'm going to pick up and talk about what discrete Fourier transform is. But first, I'm going to kind of go into what some of the applications are, so that way, as we're talking about what DFT actually is, we can kind of be imagining what some of the applications it's used for are. So first, DFT is used to perform what's known as Fourier analysis in many practical applications. So one of the big ones, there's image processing, there's digital processing, so music. So in digital processing, for example, the function is any quantity or signal that varies over time, such as pressure of a sound wave, a radio signal, daily temperature readings, and they're sampled over a finite time interval. In image processing, the samples can be values of pixels along a row or a column of an image, and also it's used efficiently to solve partial differential equations and to perform other operations such as convolutions or multiplying large integers. So next. So DFT itself says that any time domain function f can be any time domain function f can be decomposed into a frequency domain coefficients. And here we see that in f hat. In f hat. Let's see here. Sorry about that. So next, we see DFT is used to convert a finite sequence of equally spaced samples of a function into an equivalent length sequence of equally spaced samples of the discrete time Fourier transform, which is a complex valued function of frequency. So here at the bottom, I just have an image that we created just to show that where we take a time domain, and through DFT we move into the frequency domain. And up on the top right, we just mentioned that that DFT is said to be a frequency domain representation of the original input sequence, and the output has the same sample values as the original input sequence. So once again, we kind of show that in the picture. We have n to n minus 1 in the time domain, and then we have n to n minus 1 in the frequency domain. So the input size is equivalent to the output size, except for they are transformed through DFT. So next we move on to FFT, which is the fast Fourier transform, which is a fast computational algorithm in order to compute this discrete Fourier transform. So our goal is to use FFT in order to transform or to compute using FFT to compute DFT. FFT can be used to name any efficient algorithm that can compute DFT in big O of n log n time instead of big O of n squared time. So as Hector was mentioned at the beginning of the presentation, usually when we're multiplying these polynomials, that is done in big O of n squared time. But any FFT algorithm is able to compute this in big O of n log n time. So there are several FFT algorithms. We just listed a few of them here. We have Cooley-Tukey, prime factor FFT algorithm, and then I'm not sure how to pronounce this one, maybe Brunn's FFT algorithm are just a few examples. So next, why do we need FFT? So, or one of the benefits of FFT, and I kind of mentioned that in the last slide, but it all comes down to complexity. The straightforward method of computing DFT, or the direct method, adding to polynomials of degree n takes big O of n time, and multiplying two polynomials takes big O of n squared time. So as we mentioned before, FFT can reduce this time to multiply polynomials down to big O of n log n, which is extremely important when it comes to digital and image processing. We can really reduce the time it takes to compute the DFT. So next, we have the runtime analysis. We've kind of just created a graph here. The blue, as you can see, you want to pick up here from Hector?
Yeah, the blue here, it shows just a standard DFT running time of a DFT, and the green shows the running time of an FFT algorithm, and it's just n log n. So it's n log n versus n squared. It's very obvious which one wins here.
Yes, we can easily see the significance in the change of time to compute in order to for each of these algorithms.
All right, so we have the pseudocode for recursive FFT, and notice that the only parameter that gets passed into the FFT is this a value. And now, what is this a value? The a value is, turns out that it's a vector of all the
coefficients, right?
The coefficients of the function that you're going to be analyzing or transforming. And here n is equal to the length. How Austin mentioned, the input has the same number of input values as the output value. So n here is going to be the length of our coefficients. And line 2 just says if n is equal to 1, just return a. That's your base case. So before you move on, you want to test your base case. Otherwise, we use the complex roots of unity, and lines 4, 5, and 13 guarantee that omega is updated properly, so that whenever lines 11 through 12 are executed, we have omega equals omega to the k raised to the k of n. All right, and now lines 6 and 7.
And just to mention also, and this allows it to keep a running value of omega from iteration to iteration, which ends up saving us time in the end.
Yeah, thanks, Austin. All right, now let's move on with the next few lines of code. Lines 6 and 7. These are vectors. And now, what are these vectors? So the superscripts actually represent even and odd, respectively. And so we have, quote unquote, a vector or a list of these coefficients. Now, we got these coefficients from the parameter that we passed into the FFT algorithm. And so the algorithm just breaks it down. It looks at which coefficients are even and which ones are odd, and it stores them into this new vector. And then 8 and 9 calls the function, the same function recursively, and passes in the respective even and odd parameters into the recursive form.
And that continues to happen, right, Hector? Until those line 8 and 9 continue to be called until we reach the base case, which allows after each one reaches its base case is able to build back out and to give us our solution.
Yes. All right, and now we're on line 10. Now line 10 hits the for loop, and give us 1 second here.
Let's see here. We're just making sure.
All right, now we hit the for loop, and lines 11 and 12 multiply each value y of k by omega times raised to the kth power. And you see how, you know, each iterator of that for loop raises the power of, does it raise the power of omega? No, it doesn't. So basically line 11 adds this product to yk of 0, and line 12 subtracts it because we use each factor omega raised to the k of n in both its positive and negative forms. And we call the factors omega raised to the k the twiddle factors. And last but not least, we, you know, the for loop finishes up, and then we return the result, which is the, you know, it's going to be the function, the output function is going to be whatever we want it to convert our domain function.
Yes, and y will be the input set, but converted into y is basically, we can think of it as an array, but is a column vector, for example, which we took the input values a given, and for example the time domain, and we return y, which are this is the new set of those values, but in the frequency domain. And to determine the running time of recursive FFT, we note that that exclusive of the recursive calls, each invocation takes time of big O of n, where n is the length of the input vector. So for us, that would be a. So the recurrence for the running time is therefore big O of n log n. So now we can say that we can evaluate a polynomial of degree bound n at the complex nth roots of unity in time of big O of n log n using the fast Fourier transform. So that is all for today's presentation, and we will be giving this presentation tomorrow in class. Thank you.
Thank you for listening. You make sure to give us a thumbs up.